Imagine a world shrouded in a thick orange haze. Imagine a world shrouded in a thick orange haze. This isn't a planet from a science fiction novel, it's a real place, orbiting the majestic ringed planet, Saturn. I'm talking about Titan. This moon is one of the most fascinating objects in our entire solar system. It holds secrets that challenge our very understanding of what a world can be. It has an atmosphere thicker than Earth's. It has liquid flowing on its surface. But this isn't water. This is a place where science fiction becomes science fact, and every new discovery just deepens the cosmic mystery. What makes Titan so utterly compelling? It's the tantalizing possibility that it mirrors a very young, primordial Earth. Billions of years ago, before life took hold on our own planet, Earth might have shared some characteristics with the Titan we see today. It's a cosmic time capsule, frozen at a chilling -179 degrees Celsius. Here, the chemical processes that could potentially lead to life are happening right now, but at an incredibly slow, cryogenic pace. We look at Titan, and we're not just seeing a moon of Saturn. We are peering into a laboratory of prebiotic chemistry, a place where the building blocks of life might be forming in an environment that is both strangely familiar and profoundly alien. Let's talk scale. When you look up at our own moon in the night sky, it seems pretty big, but Titan would dwarf it. In fact, Titan is larger than the planet Mercury. It's the second largest moon in the entire solar system, bested only by Jupiter's moon Ganymede. This isn't just some small dead rock floating in space. Titan is a planetary-scale body with its own complex systems. Its sheer size means it has enough gravity to hold onto a substantial atmosphere, which is a rare feat for a moon. This gravitational muscle is the first key ingredient in making Titan extraordinarily special. Its diameter stretches over 5,150 kilometers. Let's put Titan in its place. It orbits Saturn, the gem of the solar system, at a distance of about 1.2 million kilometers. It takes Titan just under 16 Earth days to complete one orbit. And just like our moon is tidally locked to Earth, Titan is tidally locked to Saturn. That means one side of Titan perpetually faces the magnificent ringed planet. Imagine the view from that side of the moon. Saturn would dominate the sky. This constant gravitational dance also shapes Titan's internal structure and geology. The surface of Titan itself remained a complete enigma for a very long time. Why? Because of that thick, uniform orange smog that cloaks the entire moon. This atmospheric haze is made of complex organic molecules called tholins, created when sunlight interacts with the upper atmosphere. Let's dive into that atmosphere. Titan's atmosphere is, in a word, exceptional. It's the only moon in our solar system with a dense atmosphere. And when I say dense, I mean it. The surface pressure on Titan is about 1.5 times that of Earth at sea level. If you were standing on Titan's surface, without a spacesuit, you'd be instantly frozen and have nothing to breathe, but let's ignore that. The pressure itself would feel surprisingly familiar. It would be like being at the bottom of a swimming pool about 5 meters deep. This thick atmospheric blanket is also why the moon is so hazy and why its surface is so hard to see from space. The composition of this atmosphere is the most intriguing part. It is overwhelmingly nitrogen, just like Earth's. About 95% of Titan's atmosphere is nitrogen, while Earth's is about 78%. But that's where the similarity ends. The rest of Titan's atmosphere is mostly methane, with small amounts of other hydrocarbons like ethane. There's virtually no free oxygen. This chemical cocktail, energized by sunlight, is what creates the organic haze, the tholins, that gives Titan its signature pumpkin orange color. It's a massive, planet-sized chemical factory. The sheer thickness of this nitrogen-rich sky has some weird effects. Because the atmosphere is so dense and Titan's gravity is so low, about 1/7 of Earth's, you could theoretically fly through its skies. If you had a pair of wings strapped to your arms, a good running start would be enough to get you airborne. On Earth, we have a water cycle. Water evaporates from oceans, forms clouds, rains down, and flows back to the oceans through rivers. It's a process fundamental to our planet's climate and biology. Now take that entire concept, but replace water with liquid natural gas. That's what's happening on Titan. This moon has a complete active hydrological cycle based on methane-ethane. At Titan's frigid temperatures, methane can exist as a solid A liquid and a gas, just like water does on Earth. This simple fact allows for a weather system that is both surprisingly familiar in its mechanics and astonishingly alien in its substance. Imagine vast, dark lakes and seas, not of water but of liquid methane-ethane. These are concentrated in Titan's polar regions, where the temperatures are just right to allow the liquids to pool. Radar map, Titan's North Pole, Kraken Mare and Ligeia Mare labeled. The largest of these seas, Kraken Mare, is enormous. It's larger than all of North America's Great Lakes combined. Another, Ligeia Mare, is so deep and so transparent to radar that for a long time we couldn't even see its bottom. These aren't just puddles. They are massive bodies of liquid hydrocarbons with coastlines, bays, and islands. When it rains on Titan, it's not just methane that falls from the sky. The sunlight-driven chemistry in the upper atmosphere creates more complex organic molecules, heavier hydrocarbons, tholins. This constant, gentle drizzle of organic material has been happening for billions of years, a slow, steady accumulation blanketing an entire world. The material settles everywhere, mixing with the water-ice bedrock, and getting sculpted by Titan's weather. It's a key part of the moon's surface geology, creating some of its most distinctive and mysterious features. One of the most stunning discoveries was vast fields of gigantic dunes. These are not made of silicate sand like the Sahara. Instead, they're composed of dark hydrocarbon grains, particles of solid organic tar, or plastic-like material. These dunes are enormous, some reaching hundreds of meters high, and stretching for hundreds of kilometers. They're primarily found in the equatorial regions, forming a dark belt that encircles the moon. The shape and orientation tell us about prevailing winds on Titan. Those winds appear to blow from west to east. The dunes presented a puzzle. The measured surface winds are actually quite light. So how could gentle breezes build such massive structures? The answer lies in a combination of factors. Titan's low gravity. The particles themselves might be stickier than Earth sand. Occasional, more powerful storms, and seasonal wind shifts that kick things into motion. Together, over geological time, they can build these dunes. These dark, oily sands are the direct result of atmospheric chemistry raining down and being shaped by the moon's climate. A landscape of hydrocarbon dunes. At first glance, Titan and Earth seem to be worlds apart. One is a frigid moon orbiting a gas giant with a surface temperature cold enough to freeze air. The other is a temperate, rocky planet orbiting a star, teeming with life. And yet, the more we study Titan, the more it looks like a bizarre, funhouse mirror reflection of our own planet. The similarities are striking and profound. Both worlds have dense, nitrogen-rich atmospheres. Both Earth and Titan have active weather systems driven by a liquid cycle. On Earth, it's water. On Titan, it's methane. Show side-by-side water versus methane cycle diagram. Evaporation, cloud formation, precipitation, flowing liquid that carves channels, rivers, and deltas. Seas, lakes, shorelines changing with the seasons, surfaces shaped by wind-rain tectonic activity. On Titan, that tectonics involves shifting plates of solid water ice. These parallels show that the laws of physics create similar patterns across the cosmos, even when the ingredients are wildly different. For centuries, Titan was just a fuzzy orange dot in our telescopes. We knew it was big, and we knew it had an atmosphere. But that was about it. Everything changed with the Cassini-Huygens mission. This was a joint venture between NASA, the European Space Agency, the Italian Space Agency. The Cassini orbiter was designed to study Saturn and its system for years, while the Huygens probe was designed to detach from Cassini, plunge through Titan's atmosphere, and land on its mysterious surface. This was humanity's first and so far only attempt to land on a world in the outer solar system. On Christmas Day 2004, the Huygens probe separated from its mothership, Cassini. It coasted toward Titan for 3 weeks. Then, on January 14, 2005, it hit the top of the atmosphere at incredible speed. For the next 2.5 hours, it was a dramatic descent under parachute. As it drifted down, its instruments were whirring, sniffing the chemical composition of the air, measuring wind speeds, taking pictures. The data it sent back was a revelation. This is the big question, isn't it? Could there be life on Titan? When we look for life elsewhere, we usually follow the water. But Titan forces us to think outside that box. Life as we know it seems impossible on the surface. It's far too cold for liquid water, methane, ethane. Not great solvents for the kind of chemistry that powers life on Earth. So if we're looking for Earth-like life, the surface of Titan is probably not the place. But what about life not as we know it? Could some form of exotic life exist in the liquid methane seas? This is a fascinating area of speculation. Scientists have theorized about life forms with a completely different biochemistry. Instead of having water-based cells, they might have azotosomes, cell-like membranes made from nitrogen compounds that could function in liquid methane. These hypothetical organisms wouldn't breathe oxygen. They might breathe hydrogen and metabolize acetylene, creating methane as a waste product. We've even seen some tantalizing, though inconclusive, chemical signatures in Titan's atmosphere that could be consistent with this kind of life. It's a long shot, but the possibility is mind-bending. The Cassini-Huygens mission gave us a revolutionary first look at Titan, but it left us with more questions than answers. It was like reading the first chapter of an epic novel. We know the setting and the main characters, but we have no idea how the plot will unfold. What are the dunes really made of? What is the chemistry of the lake beds? Do the magic islands hint at geological activity? And the biggest question of all, are the ingredients for life actually turning into something more? To answer these questions, we can't just orbit. We have to go back to the surface and explore, and that's exactly what NASA plans to do. The next chapter in Titan exploration is a mission called Dragonfly. It is one of the most exciting and innovative missions ever conceived. Dragonfly is not a rover, it's not a lander, it's a relocatable drone, a dual quadcopter about the size of a small car. Taking advantage of Titan's low gravity and thick atmosphere, Dragonfly will be able to fly from one location to another. It will be able to take off, fly for miles, and then land to study a new site. This gives it incredible mobility, allowing it to explore diverse geological settings that a rover could never reach. Dragonfly is scheduled to launch in 2028 and arrive at Titan in the mid-2030s.